Welcome to the world of data wrangling and preprocessing. In this video, we'll explore the essential steps that data scientists take before any analysis can begin. Data wrangling is the process of cleaning and transforming raw data into a usable format. It's often said that data scientists spend most of their time here, making sure the data is accurate, consistent, and ready for modeling. We'll cover techniques for handling missing values, identifying outliers, formatting inconsistent data, and feature engineering. Let's dive into the journey of turning messy data into valuable insights. Data wrangling is crucial because raw data is rarely perfect. It often contains errors, inconsistencies, and missing information that can lead to inaccurate results if not addressed. By carefully cleaning and organizing data, we ensure that our analyses and models are built on a solid foundation. This process not only improves the quality of insights but also saves time and resources in the long run. Understanding the importance of data wrangling sets the stage for all the steps that follow in the data science workflow. Before we can analyze data, we need to identify common issues that might exist. These include missing values, outliers, duplicate entries, and inconsistent formatting. Each of these problems can distort our analysis if left unaddressed. Recognizing these issues early allows us to apply the right techniques to clean and prepare the data. In the next scenes, we'll look at each of these challenges in detail and discuss practical solutions for handling them effectively. Missing values are a common problem in real-world datasets. They can occur for many reasons, such as errors during data collection or entry. There are several strategies to handle missing data, including removing rows with missing values, filling them with the mean or median, or using more advanced imputation techniques. The choice depends on the nature of the data and the amount of missing information. Addressing missing values ensures that our analysis remains robust and reliable. One straightforward way to handle missing values is to remove any rows that contain them. This method is simple and effective when only a small portion of the data is missing. However, if too many rows are removed, we risk losing valuable information. It's important to weigh the pros and cons before deciding to drop data. In cases where missing values are widespread, other strategies may be more appropriate. Another common approach is to fill missing values with the mean or median of the column. This technique works well when the missing data is random and not too extensive. Using the mean is suitable for normally distributed data, while the median is better for skewed distributions. Imputation helps retain more data for analysis, but it's important to remember that it introduces some assumptions about the data's distribution. For more complex datasets, advanced imputation methods like regression, k-nearest neighbors, or machine learning models can be used to estimate missing values. These techniques consider relationships between variables to make more informed guesses. While they can improve accuracy, they also require more computation and careful validation to avoid introducing bias. Choosing the right imputation method depends on the dataset and the analysis goal. Outliers are data points that differ significantly from others in the dataset. They can result from errors, unusual events, or natural variation. Identifying outliers is important because they can skew results and affect model performance. Common methods for detecting outliers include visualizations like box plots, statistical tests, and z-scores. Once identified, we need to decide whether to remove, correct, or keep these values based on their context. Visual tools like box plots and scatter plots make it easier to spot outliers in your data. Box plots show the distribution and highlight values that fall outside the typical range. Scatter plots can reveal unusual patterns or points that don't fit the trend. Visualization helps us quickly identify potential problems and decide on the best course of action for each outlier. Statistical techniques like calculating z-scores or using the interquartile range (IQR) help identify outliers mathematically. The z-score measures how many standard deviations a value is from the mean, while the IQR focuses on the middle 50% of the data. Values that fall far outside these ranges are flagged as outliers. These methods provide a systematic way to detect anomalies in large datasets. Once outliers are identified, we need to decide how to handle them. Options include removing the outlier, correcting it if it's an error, or keeping it if it represents a valid but rare event. The choice depends on the context and the impact on analysis. Removing outliers can improve model accuracy, but sometimes they provide valuable insights into unusual patterns or behaviors. Duplicate entries can occur when data is collected from multiple sources or entered more than once. These duplicates can inflate results and lead to incorrect conclusions. Identifying and removing duplicates is a key step in data cleaning. Most tools offer functions to find and drop duplicate rows, ensuring each observation is unique and the analysis is accurate. Inconsistent formatting is another common issue, especially when data comes from different sources. This can include variations in date formats, capitalization, or units of measurement. Standardizing formats is essential for accurate analysis. Tools and scripts can help automate this process, making sure all data follows the same conventions and is easy to work with. Dates can be formatted in many ways, such as DDYYY or DDMMYYY. Mixing formats can cause confusion and errors in analysis. Standardizing all dates to a single format ensures consistency and makes it easier to sort, filter, and analyze time-based data. Most data tools provide functions to convert and unify date formats efficiently. When working with numerical data, it's important to ensure that all values use the same units of measurement. For example, mixing centimeters and inches can lead to incorrect calculations. Converting all measurements to a common unit prevents errors and simplifies analysis. Always check for unit consistency when merging or comparing datasets. Text data often contains inconsistencies like different capitalizations, extra spaces, or typos. Cleaning text involves standardizing case, trimming whitespace, and correcting common errors. This step is especially important for categorical data, where variations can create unnecessary categories and complicate analysis. Feature engineering is the process of creating new variables or features from existing data to improve model performance. It's a creative and critical step in data preprocessing. By combining, transforming, or extracting information from raw data, we can highlight patterns and relationships that models can learn from more effectively. One way to enhance your dataset is by creating new features. For example, you might combine two columns to form a new variable or extract the year from a date column. These new features can provide additional context and help models make better predictions. The key is to think creatively about what information could be useful for your analysis. Transforming existing features can help models learn more effectively. This might involve scaling numerical values, encoding categorical variables, or applying mathematical functions. For instance, normalizing data ensures that all features have the same scale, which is important for many algorithms. Proper transformation can make a big difference in model performance. Many machine learning algorithms require numerical input, so categorical variables must be converted into numbers. Common encoding techniques include one-hot encoding and label encoding. One-hot encoding creates a new column for each category, while label encoding assigns a unique number to each category. Choosing the right method depends on the algorithm and the data. Scaling and normalization are important for algorithms that are sensitive to the range of data. Scaling adjusts values to a specific range, such as 0 to 1, while normalization ensures that all features contribute equally to the analysis. These techniques help prevent features with larger values from dominating the results and improve model convergence. Dates often contain valuable information that can be extracted as new features. For example, you can create variables for the year, month, day of the week, or even whether a date falls on a weekend. These features can help models capture seasonal patterns or trends over time, adding depth to your analysis. Binning involves grouping continuous numerical values into categories or bins. For example, ages can be grouped into ranges like 018, 1935, and so on. Binning can simplify analysis and help models detect patterns that might be missed with raw numbers. It's especially useful when the relationship between the variable and the target is not linear. Not all features are equally useful for analysis. Feature selection is the process of identifying the most relevant variables for your model. By removing irrelevant or redundant features, you can improve model performance and reduce complexity. Techniques for feature selection include correlation analysis, recursive elimination, and using model-based importance scores. Correlation analysis helps identify relationships between variables. Highly correlated features may provide redundant information, so it's often beneficial to keep only one of them. By examining correlation matrices, we can spot which variables move together and make informed decisions about which features to include in our models. Recursive feature elimination is a technique that systematically removes the least important features and evaluates model performance. By repeating this process, we can identify the smallest set of features that still provides strong predictive power. This method helps streamline models and avoid overfitting. Some machine learning models, like decision trees, can provide importance scores for each feature. These scores indicate how much each variable contributes to the model's predictions. By focusing on the most important features, we can build simpler and more effective models. Always validate feature importance with domain knowledge and additional testing. Transforming data can help reveal patterns and relationships that aren't obvious in the raw form. Common transformations include logarithms, square roots, and polynomial features. These techniques can make data more suitable for certain models and improve predictive accuracy. Always consider the impact of transformations on interpretability. Skewed data can affect the performance of many algorithms. Applying transformations like log or square root can help normalize the distribution and make patterns more apparent. It's important to visualize the data before and after transformation to ensure the changes are beneficial. Sometimes, valuable information is spread across multiple datasets. Combining them through merging or joining can provide a more complete picture. It's important to ensure that the datasets are compatible and that keys used for merging are consistent and unique. Properly combined data can unlock new insights and improve analysis. Consistency is key when working with combined datasets. Check for matching column names, data types, and units. Resolve any conflicts before analysis to avoid errors and ensure accurate results. Consistent data is easier to work with and leads to more reliable conclusions. Validation checks help ensure that data meets quality standards before analysis. These checks can include verifying ranges, checking for missing or duplicate values, and confirming that formats are correct. Automated validation scripts can save time and catch errors early in the process. Keeping a record of all data cleaning steps is essential for reproducibility and collaboration. Documenting changes ensures that others can understand and replicate your process. Good documentation also helps track the impact of each step on the final results. Automation can streamline repetitive data cleaning tasks and reduce the risk of human error. Scripts and workflows can handle missing values, outlier detection, and formatting consistently every time. Automation frees up time for more complex analysis and ensures that pre-processing steps are applied uniformly. There are many tools available for data wrangling, from spreadsheets to specialized software like Python's Pandas or R's Deepler. These tools offer powerful functions for cleaning, transforming, and analyzing data efficiently. Choosing the right tool depends on the size and complexity of your dataset, as well as your workflow preferences. Following best practices ensures that your data wrangling process is efficient and reliable. These include starting with a clear plan, validating each step, and documenting your work. Regularly reviewing your process helps catch errors early and maintain high data quality throughout your project. Data wrangling is often a team effort, especially on large projects. Collaboration tools and version control systems help teams work together efficiently. Sharing code, documentation, and clean datasets ensures everyone is on the same page and can contribute effectively. Reproducibility means that others can follow your steps and achieve the same results. This is critical in data science for building trust and verifying findings. Keeping code, data, and documentation organized makes it easier for others to reproduce your work and build on it in the future. Handling data, especially sensitive information, privacy, and security are top priorities. Always follow best practices for data protection, such as anonymizing personal information and using secure storage solutions. Respecting privacy builds trust and ensures compliance with regulations. Even experienced data scientists can make mistakes during data wrangling. Common pitfalls include overlooking missing values, ignoring outliers, or failing to document changes. Being aware of these risks helps you avoid them and maintain high data quality throughout your project. Data cleaning is rarely a one-time task. As you explore and analyze your data, new issues may arise that require additional cleaning. An iterative approach allows you to refine your dataset over time, ensuring that it remains accurate and useful for analysis. Regularly evaluating data quality helps ensure that your analysis is based on reliable information. Key metrics include completeness, accuracy, consistency, and timeliness. High-quality data leads to better models and more trustworthy insights. Once data is cleaned and features are engineered, it's time to prepare it for modeling. This includes splitting the data into training and testing sets, scaling features, and ensuring that all pre-processing steps are applied consistently. Proper preparation sets the stage for successful model building. Before moving on to modeling, review all pre-processing steps and perform final checks. Make sure that missing values, outliers, and inconsistencies have been addressed. Confirm that features are properly engineered and documented. A thorough review ensures that your data is truly ready for analysis. Summary: data wrangling and preprocessing are foundational steps in any data science project. By handling missing values, identifying outliers, formatting data consistently, and engineering useful features, we set ourselves up for success. Clean, well-prepared data leads to more accurate models and better insights. Remember, the time invested in preprocessing pays off throughout the entire data science workflow.